Thank you very much to the organizers for a very kind invitation for me to share some of the exciting and, I must say, caveat, work in progress about categorification and formalizing some natural phenomena, which I will very broadly describe as diffusion. So the first place you might encounter, and I should say this is joint work with Robert Griest, who was my doctoral advisor, and also Miguel Lopez and Paige Randall Norris. So sort of the outline of my talk is we're going to discuss some competing views of diffusion from the perspective of physics, from the perspective of graph theory, and then also from the perspective of what I might call combinatorial or computational topology. And then we'll describe a nice construction, which I refer to as network sheaves, which generalizes a few of the different Laplacians that we've seen in the previous section of the talk. So these Laplacians include, if you're familiar, the graph Laplacian, the graph connection Laplacian, which is a discretization of the connection Laplacian that some of you might be familiar with in geometry. So we're going to introduce network sheaves and describe a Laplacian for these sheaves. And then we're going to describe how we can generalize this in a different setting, where instead of working in the category of Hilbert spaces, where everything is nice and we have this huge corpus of knowledge to do analysis with, we're going to instead work in quantile enriched categories, where our enriching object are quantiles, which are lattices with a monoidal structure. And then we're going to describe what these categories look like, give some examples of them, and then finally describe weighted limits and co-limits, which in this case are simply meets and joints in the lattice theoretic sense. And then finally, we get into the real, the meat of things. We'll describe network diffusion in this categorical perspective. So we'll describe what weighted global sections are. So these are global sections up to a certain choice of weight in our quantile. And then we'll describe a Laplacian, which is, this is a generalization of some of the work I did during my doctorate, but this is a Laplacian we might call the Tarski Laplacian. And we describe a theorem which is very similar in style to the Hodge theorem, which we might call the Hodge-Tarski theorem, which describes an isomorphism between global sections and certain points that are fixed by the Laplacian. And then we might describe, towards the end, some applications of all this work for particular choices of quantiles. So first of all, what is diffusion? So one way to think about diffusion is from the physical point of view. So diffusion is a central concept in thermodynamics, and it describes the change in temperature or gradient, concentration gradient, for some source of energy that's being distributed in some space, for instance, some surface of the table, a water bottle. And as we've probably learned in our undergraduate PDE course, that there's an equation called the heat equation, which models this change in temperature or concentration over time. And this Laplacian is really defined on Euclidean spaces, or subsets, nice subsets of those Euclidean spaces. So this work has been generalized in Hodge theory, or in just really differential topology to manifolds. So suppose we have some Riemannian manifold, and we can form the Rham complex, which I'm sure is familiar to most of you, where each of the cochains in our Rham complex are differential K-forms. And our coboundary operator of this complex is the exterior derivative. So in this framework, we have a cochain complex that we boundary square, or coboundary square to 0, and we can form the Hodge Laplacian delta, which is equal to the linear adjoint composed with, it's the formula over here. So we have a Laplacian, and in particular, the Hodge theorems, we have a decomposition. So anytime we have a K-form, we can decompose it as a element of the image of D, an element of the image of D star, and then what's considered a harmonic form, which is an element of the kernel of delta. And one of the takeaways of this Hodge decomposition is that, well, first of all, we only really required this to be a cochain complex. The fact that these are very nice, smooth structures isn't actually important. It's a purely algebraic result. We do require that we're working in Hilbert spaces, however. We need inner products, or at least maybe not Hilbert spaces, but pre-Hilbert spaces to be kind of technical. So in this case, we have an isomorphism between the cohomology and the kernel of the Hodge Laplacian. So this is what I might refer to as the Hodge theorem. And one of our goals is to generalize this theorem in an enriched categorical context. Another perspective which I hold near and dear comes from graph theory. So in this talk, we're going to be thinking a lot about graphs, and our notation for graphs is we have a set of vertices and edges denoted x naught and x1. So we assume our graphs are undirected, and they have some n number of nodes. And in the context of graph diffusion, we typically consider some labeling function on the graph, which by on the graph, I mean on the nodes of the graph. So this perhaps is measuring some quantity. Maybe you have a sensor network and you're measuring the displacement of the ground. This is a project I'm actually working on with a geologist, but we can have many kinds of networks with some sort of signals on them. It's a very natural thing to think about in engineering. As I should say, I wear a few different hats. One of them is as a mathematician, which I'm wearing today, but from time to time, I'll take that hat off and put my engineer hat on. So we say, in this notation, two nodes are adjacent if there's an edge that co-bounds them. And in this sort of classical spectral graph theory, we have an adjacency matrix, which is a matrix of zeros and ones. And we put a 1 whenever two nodes are adjacent, and it's a 0 otherwise. And so if we consider a random walk where we initialize at some random node, arbitrary node rather, in the graph, and then we decide to move to an adjacent node with probability 1 over the degree, so we're, in this case, very simple case, we're equally as likely to move somewhere else, then we get this Markov chain with a transition matrix P. And it turns out that if you sort of normalize this matrix, you get something that is very much like a Laplacian. And this Laplacian can also be written as a boundary transpose, just like the Hodge Laplacian. So in continuous time, we have a heat equation, but instead of having functions on a whole space, we have signals or real-valued functions on the nodes of a graph. And there's definitely a relationship between the two perspectives. So there's some really interesting work by Mikhail Belkin and Nyogi, as well as Amin Singer and Wu, which describe a very specific relationship between the discrete case where we have a graph and the continuous case where we have some manifold. And the way to go between those two perspectives, as you might imagine, is we sample a bunch of points from the manifold, and then we connect points that are within some threshold distance. So we're able to go back and forth between the continuous and the discrete world. For now, however, in an effort to sort of formalize all this with category theory, we're going to live mostly in the discrete world, and perhaps it is an open question or a future direction how we can move back to the continuous world at some point. So here's sort of a picture of what graph diffusion might look like. So we have, let's say, colors that represent sort of the temperatures of these various nodes, and we have information is sort of passing between the nodes of a graph, and eventually we get this process where we even the temperature reaches an equilibrium where all the states are somewhere near an orange hue. So this is a little animation I made during my PhD that I thought you might enjoy. So the story doesn't end, actually, with graph diffusion. So we considered only scalar valued signals on the graph, but often we want to consider vector valued signals. So a very natural example here is, for instance, my example with the GPS sensor network. So we have GPS sensors. For instance, in New Zealand, there's sensors that are trying to monitor earthquakes, and each sensor has a reading every day or so of the displacement in altitude, so up and down, east and west, north and south. So this is an example of a vector valued signal on the graph, because we can think of all these sensors as forming networks. And in this case, we actually, this was discovered by Singer and Wu, that we can discretize what's known as the connection Laplacian from geometry, which, if you want to know the details, is you can find it in the theory of elliptic PDEs. But this graph connection Laplacian is the discretization of that. And the way that this works is we have a block matrix given by A of VW. So there's blocks for each pair of nodes, V and W. And the way it works is we have a orthogonal matrix OVW that is an approximation for a parallel transport for a tangent vector XV to a tangent vector XW. And then finally, so we parallel transport adjacent nodes, and then we take a weighted sum of this parallel transport. So this is ultimately our inspiration for how to categorify this, because we want to be able to define something that is similar to parallel transport in this context of quantile enriched categories, but also be able to aggregate things. So take various vectors that we've transported and average them. And I should also say this is sort of a picture you get here. So we have a manifold, probably a sphere, and for each point, maybe we sample from the manifold. We have a tangent space, and we have two orthogonal maps, one that sends a tangent vector of this tangent space to a tangent vector of a nearby tangent space. And then we also have the inverse, which is also the transpose of this map that takes it back. So what we'll be doing is defining in this graph connection Laplacian is we apply parallel transport to all of our sort of neighbors in a neighborhood, and then we take a weighted sum. We average everything together. And maybe the weight is determined by the distances, either on the manifold or maybe as geodesic distances, or maybe they're just Euclidean distances. And then the final perspective I want to share is from computational topology. So often in data science, if you're given a data set with vectors in a large dimension, it's often useful to understand what the topology of that data looks like. So if I build a simplicial complex, for instance, to approximate the data, I can calculate what the homology of that simplicial complex will be. And it turns out that it's also useful to calculate this using a Laplacian, because we have this Hodge theorem, remember, that the kernel the cohomology, okay, we're working with, we have an isomorphism between dual vector spaces. But the kernel of the cohomology is isomorphic to the kernel of the Hodge Laplacian is isomorphic to the cohomology. So this is a way to compute features that are topological from data. And so in sort of the intellectual history of this project, you can sort of extend this theory of this combinatorial Hodge Laplacian and this connection Laplacian are all special instances of what were called cellular sheaves, which were introduced by Justin Curry and also worked with by my advisor, Robert Greist, and Jacob Hansen. So network sheaves, I'm going to give you the most general definition. So suppose we have a graph, and this theory holds for more general spaces, but I think graphs are the most enlightening thing to think about here. And suppose JOP is a small category, it's just a partial order that indexes whenever a node of a graph is incident to an edge of the graph. In this partial order we get by closing these incidence relations. And so suppose C is a category where we want our data to live in. So a network sheaf on X, maybe I should say presheaf, is a functor from JOP to C. So it's just a presheaf on JOP, valued in this category C. And a cosheaf is the opposite. So instead of having maps that go from nodes and data living above nodes to edges, we have maps going from data living above edges to data living above nodes. And in the typical language, we say a stock is this functor evaluated at V. So it's a particular object, which we call a stock. And these maps, we use the nomenclature of sheaf theory, the theory restriction, and maybe co-restriction maps. And then given this functor, as long as this category C is complete, you can form a cone underneath it and form a limit. So the global sections of F is defined as being this following limit. And this is a particular isomorphism, or a particular object in the isomorphism class of this limit. And for those of you who might wonder, are we actually doing sheaf theory? We actually are doing sheaf theory, because if we take this category J, this post set, and we put a topology on it, that Justin Curry proved in 2014 that this category of sheaves over this topology is equivalent to just this functors, the presheaves. So we are in fact doing sheaf theory, but it's not so important that we are. So this is sort of a picture of what this looks like. We have data over vertices, data over edges, and our base space is a graph. So one particular example of this is if the category C of data is, let's say, the category of pre-Hilbert spaces. And a network sheaf is a functor from JOP into Hilbert spaces. And a cosheaf, a natural cosheaf to think about is we just take the adjoint of every linear map that is exhibited in the sheaf. So once we do that, we can define the sheaf Laplacian as follows. So this sheaf Laplacian turns out to be the Hodge Laplacian of a cochain complex that you can build from this following boundary or co-boundary operator. And this co-boundary operator is very simple. All we do is we look around at a neighborhood and apply our restriction maps. And we take a alternating sum of these depending on what orientation we place on the edges. And unsurprisingly, the orientation doesn't matter. So we get this really nice theory where we have a Laplacian for these network sheaves, and we get a heat equation as a result. So this is a theorem of Riess and Hansen, and also in the general case where these are Hilbert spaces and not finite dimensional Hilbert spaces, we also have recent work by Riess and Gould, which says that given an arbitrary initial condition, so we have a assignment of data to the sheaf, that the ODE x dot equals minus Lx converges to the orthogonal projection onto the global sections. So this gives us a way of actually computing global sections of a sheaf, because we can choose our favorite Euler discretization of this ODE, and we can implement this. And people have implemented it. For instance, for those of you who are there for the school part of this program, Michael Robinson has code that goes along with a lot of his work on network sheaves. So how can we take this picture and transport it to different types of data? So working with vector spaces from a practical point of view limits your applicability to data that is described by a vector space. But sometimes you have data that is more logical in nature. So we have, for instance, a syntax and a semantics over each node, and we want somehow the semantics to play with other nodes. So this really naturally leads to trying to generalize this to enriched category theory, or at the very least lattice theory. So let's describe what a quantale is. So a complete lattice, as you probably know, is a partially ordered set such that every subset of elements has a least upper bound. So it's complete in the sense that we can take joins whenever they exist, or they always exist in a complete lattice. And we can view complete lattices as categories where they're thin categories in the sense that between any two objects in the category, there's at most one morphism between those objects. So this is a very simple category to study. And as you probably can see, that this join operation is exactly the same as the coproduct in that category. And it's also true that in a complete lattice, we can always write a meet or greatest lower bound as a join of something. So we only need joins actually, because we can take up-closed sets down-closed sets and take the joins of them to obtain our meets. A quantale is formally a monoid object in the category of superlattices. But to be more specific, it's a monoid that also has this, or a complete lattice that also has the structure of a monoid that's compatible with the lattice structure. So we have this sort of distributive property between the monoid operation, which is denoted by this tensor product. There's a little typo, but that's okay. And this monoid operation gives you this tensor product. And one of the benefits of quantales is you get an internal Hom for free. So we have this internal Hom that is given by the adjoint functor theorem. And this is, in logical terms, we can think of this internal Hom as an implication. And so for the remainder of the talk, unless I say otherwise, we're just going to assume that Q is unitarily bounded, which means that the identity of the monoid is the terminal object, or the highest object of the lattice. And we're also going to assume that Q is commutative. And a lot of this probably goes through with not too much difficulty if we don't assume these things, but things are much more simpler to write down. So here's some facts about quantales, that if we have P is less than Q, multiplying on the left by some element is an order-preserving map. And furthermore, again, by the fact that right adjoints preserve limits, we get this property where we can take a meet of the right argument in the eternal Rham and take that meet outside it. So here's some familiar examples of quantals. We have locales, which as a Topos theorist, we are, not that I'm myself, I'm a Topos theorist, but this is a Topos theorist conference, so we're familiar with locales. The Boolean algebra, 0, 1, is a quantal. And then we get some examples from the theory of Lemaire metric spaces, such as the extended positive reals with addition under the opposite order, as well as the unit interval, 0, 1, with a T-norm structure. So these T-norms appear in a lot of different areas, and in particular, multi-valued logic. So we have a logic with multiple truth values, so not just true or false, but maybe kind of true, also called fuzzy logic, although I hate the term fuzzy. But this, here's 3 examples of T-norms, multiplication, this Lukasiewicz T-norm, the middle one, and then this is just the locale structure on 0, 1. Once we have a quantal, we can enrich, have a category that's enriched in it, and it consists of an objects set, which can be arbitrary, morphisms, which is in particular element of our quantal, and the composition law. So this is enriched category theory, and we can see all these definitions in whatever reference you like for that, but one is Kelly, Basic Concepts of Enriched Category Theory. So these are the axioms for an enriched category. And the case of quantals is particularly nice because we get this property, this composition law, gives us a relationship between the quantal and the Rham sets. So in the typical fashion, we can define Q functors between Q categories. So these are functors such that Rham of xy is less than or equal to Rham of f of x, f of y. And then finally, we can define Q adjunctions, which are Q functors. And since we're working in a partially ordered set, we actually get equality here, which is a nice thing to have. So here's some examples of Q categories. So in the case of 0, 1, these are preorders, and 0, 1 functors are monotone maps. So a very simple case. Now if we enrich over the extended positive reals, these categories are Lemaire metric spaces, which behave very much like metric spaces minus the symmetry of the metrics. And 0 infinity functors are the same as non-expansive mappings. So we see already with this language of Q categories, we've been able to connect to sort of theory of operators in some sense, some very weak sense, and also the theory of partial and orders and logic. So here's some more examples of Q categories that we're going to need for the remainder of the talk. So Q itself is a Q category. The objects are just the elements of Q, and the Rham sets are given by the internal Rham. That's 1. 2, if we have an arbitrary set, then we can form a discrete category by setting the objects to be that set and the Rham set to be the top element. Remember, we're a complete lattice, so we always have a top and a bottom element. And the bottom element if A is not equal to B. So top if A equals B, bottom if A is not equal to B. If C is a Q category, then we can form the opposite category of that category just by transposing the Rham sets. So this is also useful. And then finally, if we have a collection of Q categories, then we have a product of Q categories, which is given by the objects are just the Cartesian product of the objects of each Ci, and the morphisms are given by the meet of all the Hom sets of Ci from Xi to Yi. And so that example and the first example we'll use extensively for the remainder of the talk. And then finally, two more examples. We have a functor category. So given C and D are Q categories, we have a functor category between C and D, which is a Q category with objects consisting of functors. And morphisms are given by natural transformations between F and G. And if you sort of follow your nose, these natural transformations have a very simple form. They're just meets of these Hom sets obtained by applying F and G to all the objects of C. And one thing that's very nice about the theory of quantile-enriched versus just arbitrary categories enriched over some symmetric monoidal category is instead of this natural Hom set between F and G being a coend, it's just simply a meet, so we can actually compute it very simply. So it's kind of the perfect place to be, in my opinion, because you can work concretely with things, but it also covers a wide range of examples. So as expected, since we're working in Q categories, we can form limits, but instead of these limits being unweighted, we have a particular weight that we place on them. So suppose C is a category, Q category, and D is some set, and we have a diagram D over that set, valued in this Q category, as well as a weight, which assigns some particular Q to every set, to every position of the diagram. So the meet of F weighted by W is this object given by the following universal property. Similarly, we can define the join, or the weighted join, of F weighted by W is an object with a sort of dual universal property. And so this universal property utilizes the internal Hom. So in general, this definition of weighted limits is actually quite involved, but in the case of quantiles, it simplifies to just the internal Hom, and we take a meet over all the different positions in our diagram. And as we might expect, right Q adjoints preserve weighted meets, and left Q adjoints preserve weighted joints, as is true in ordinary categories. And so here's a proof. We have a right adjoint from C to C prime. Then we consider some diagram here, and we have a weight W into Q. And we utilize the fact that L and R are adjoints, as well as the fact that we can always pull, we use the universal property of the weighted meet, and as well as the fact that we can always pull meets out of the internal Homs. So it's a very nice, simple result. And so now we're ready to describe a sort of categorification of these the three or four different notions of diffusion that we described in the beginning of the talk. So for that, we're actually going to need to go to one level higher, at least briefly, of Q-enriched categories, which consist of objects and Hom sets. And these definitions are a little technical, but they allow us to define weighted limits, which we're going to need to define global sections. So the only example we really need of this is the category Q-cat underline, which is the category whose objects are Q categories, and Hom objects are natural transformations between C and D. And this allows us, whenever we have a pseudo-functor from some base category C, which will be indexing a diagram, typically, and D, which is a QCAT-CAT, then we can define the limit of F weighted by W as this following set of natural transformations. So going back to our original story, where we have co-sheaves, or co-presheaves and presheaves, we consider these co-presheaves and presheaves valued in the category of Q categories. And this, recall, is assignment of a particular Q category to every node and edge of the network, as well as a Q functor between Q categories F of V and F of E. And we also have these maps that go in the reverse direction. Finally, we consider, which is very natural in graph theory, a weight. So we have, for every two edges, or every two nodes that co-bound an edge, we have a particular element of our quantile. And this allows us, all this data allows us to define parallel transport, which will be sort of the basis for our Laplacian. So parallel transport consists of, whenever we have a path in our graph, we can apply the co-sheaf restriction map, the restriction map and the co-restriction map in alternation. So we can alternate between the restriction and the co-restriction map to always get a Q functor between any two stalks over nodes of the graph. So here's a picture of the data we have. So we have Q categories over V and E. We have a weight over edges, and we have maps that go both ways. And algorithmically speaking, this allows us to define message passing algorithms where we can take data and we push it to edges and then pull it back to other vertices. So we can do a lot of things potentially with this machinery. So one thing we can do, I think, is define weighted global sections. So this definition is a little roundabout, but in order to define weighted limits in this category, we really want to weight everything by Q. But in order to define weighted limits in a QCAT-CAT, we have to actually have QCATs being the weight. So we get around this by just defining a one object Q category and then a two object Q category delta of E, which has objects consisting of two elements for that edge, V and W, which are the nodes that co-bound the edge. And then we have the Rham sets that are given by the weights. So here we have the weight from V to W, and here the weight from W to V. And in many contexts, these two weights are going to be the same in applications. For instance, in this data, it's somehow related to the distance between two data over V and W. And so this allows us to define our global sections, our weighted global sections, as the limit in QCAT-CAT, which is a subcategory of this product category of F lower applied to all the objects of our indexing category J, which recall J consists of nodes and edges with incidence relations between them. And so we can define W global sections as elements of this, basically unraveling what that previous definition of weighted limit is. They consist of elements of this product category such that these Rham sets upper bound WVW and WWV. And these Rham sets, remember, are elements of Q, so we can always compare things. And in particular, if WUV equals 1, then we actually recover the unweighted case, where everything in a global section agrees on the nodes. But with these W-weighted global sections, we can actually control how much we want things to agree. So it's like sheaf theory, but agreement is controlled. We can control everything with the weight. And so the theorem here, I don't know if I can even call it a theorem. It's just follows from the definitions. I guess most of category theory follows from definitions at some point. But it says that the objects of these weighted limits are W global sections. And furthermore, the Rham sets between particular global sections just coincide with the Rham sets in the product category. So this is not obvious, actually, and takes a little bit of work to prove. But we get the same Rham sets as we get in the product category. So this leads to the Laplacian, which I think is sort of the pinnacle of the talk so far. And I think, so given all this data that we've described, so a presheaf, the co-presheaf, a weight, the Tarski-Laplacian is a map, which we'll see very shortly, or we see below that it's actually a Q functor between these product categories given by the following. So we apply the restriction map of the presheaf to some value xw, and then we pull that data back to a node with the co-presheaf, and then finally, in the manner very similar to the connection Laplacian, we take a weighted limit instead of a weighted average. So basically replacing parallel transport with orthogonal maps, we're replacing them with Q functors, and then we're replacing the aggregation or the weighted average with a weighted limit. So first of all, this is a Q functor, and this is sort of our picture. So we have all this data, and just work now. So we have data over V, E, W, and we ride these shoots, if you will, from a particular Q category, FW, all the way to a Q category, FV. And then we do this for every neighbor of V, so we might have other neighbors, and we take a weighted limit of all this. And what do we get? So before I say what we get, I should mention an interesting analogy that was pointed out by John Baez and also Mike Schulman, I believe, that adjunctions in the linear sense are in analogy with adjunctions in the categorical sense. And I think this is very apparent in the case of enriched category theory, because if we look at the Rham sets, in enriched category theory, we get an actual quality if we're enriching over a quantile. And in the case of the linear junctions, we get this equality between the inner product of X and Lx and Y and X and L adjoint Y. And so this is really our motivation for why we might call this the categorification. So here is our sort of main result, or we're building towards our main result. But so suppose we have a particular Q, so a particular element. So this might be our threshold for how close we want to be to a global section. Then we can denote SQL as the subcategory of this product spanned by all the X's in the product category, such that the Rham of X and L of X is greater than or equal to Q. So here's a special case. If Q is equal to 1, and if we're unitarily bounded, then there's an isomorphism or equality, because we're working on a quantile, between X and L of X. So that's sort of the special case. Or not equality. I shouldn't say equality. That's incorrect. There's an inequality. And so the lemma is the following. So in the particular case where these Q functors in the presheaf and the co-presheaf, if they agree on objects, we're assuming, but there's also an adjunction between FEV and FVE. So if we assume that these are actually Q adjoint, which this is natural to think about whenever you have profunctors. You can always, you obtain an adjunction between, by Isbell or conduality, you obtain adjunctions that way. So this comes up in a lot of cases actually, where we have an adjunction between these restriction and co-restriction maps. Then the lemma says that a particular element X is in this SQ if and only if this following inequality holds. And I don't know how I'm doing on time, but I don't think we have so much time to go over the proof. But the idea of the proof is we just use the fact that that F lower and F upper are adjoint, and then we finally use the universal property of the weighted limits. So it's a very simple proof, and so this leads to the following theorem, that given this data and adjunctions everywhere, that the weighted global sections of F are isomorphic to this S1L. So we've related the global sections of the sheaf to a fixed point X property of the Laplacian. And we can compare this, for instance, to the Hodge theorem, where we have in degree 0, the global sections is isomorphic to the kernel. So this is, in some sense, the best, or maybe not the best, but this is a categorification in some sense of this Hodge theorem. And finally, along the way, we sort of discovered that in a much more general context, if we have arbitrary Q functors, that we can obtain an analog of the Tarski fixed point theorem in enriched category theory. So this says that the Tarski fixed point theorem says that if you have a complete lattice and a monotone function from that complete lattice to itself, that the fixed points of that monotone function, they form a complete lattice. And in particular, they're non-empty. This is a really cool result, in my opinion. And we were able to sort of, as a byproduct of this work, generalize the Tarski fixed point theorem to this case of sort of approximate fixed points with this SQ notation. So the theorem says if we have a Q functor and we suppose Q has all weighted joins, then this category SQL has all weighted meets and joins, which means in the sense of enriched category theory, it's complete. And work in progress is to prove this result for categories enriched in arbitrary cosmoi. So as a corollary of this fixed point theorem, we can also say that the global sections, it's another proof of it, but has all weighted meets and joins. So we're able to say something about the sheaf itself through a Laplacian operator on that sheaf. And very briefly, I'll mention some applications of this work. So if we look at stocks that are presheaves, so this is a natural thing to think about, and in particular, if Q is a discrete category, so some set, so these are free objects in a way, then in the case of 0, 1, we actually have just power sets are stocks over vertices, and we get some nice connections to multimodal logic this way. And I wish I really had time to say more about this, but we have a Kripke semantics we can define for a network, and we can use global sections to say something about that Kripke semantics. So you can read more about that in a paper by myself and Riess. In the case of Q equals the extended real numbers, we can actually solve synchronization problems in tropical or max plus algebra. So that's an interesting application. And then finally, this is sort of work in progress with Riess and Lopez. When Q is 0, 1 with some Q norm, we're working on a formal concept analysis. So this is a sort of an ontological application that's distributed. So we have, think of tables with binary relations between objects and attributes over a network, and somehow we can pose agreement and disagreement problems with this Q-enriched category theory. And then finally, something I've been working on for a while is preference dynamics. So humans tend to have preferences over the kinds of food they like, or candidates, political candidates. And I've been able to show that we have preferences that are valued in Q, that they form Q categories, and we can describe algorithms, message passing algorithms for people discussing various preferences with each other, and maybe changing their preferences after a discussion in this framework as well. So I think I'll open the floor for some questions for you all.